crazy, isn't it? When you think about how much potential in AI just gets stuck.
Yeah.
Like, a ton of machine learning projects never actually see the light of day. And then there's all that data, business data, mountains of it, just sitting unused.
Right.
Today, we're going to dig into why that is. We're talking about the AI optimization bottleneck.
That's a great way to pick it. It's like, imagine trying to build this really complex machine.
Right.
You've got all the parts, the plans are perfect.
Uh-huh.
But there's this one tiny gear somewhere in the whole system that just isn't working right.
Oh, I see.
And that one gear slows everything down. I mean, maybe even brings the whole process to a standstill.
Right.
The AI optimization bottleneck. It did all the places in AI development, all the points where things get held up. And it keeps us from creating that super powerful, super accurate AI we're all working towards.
The AI we need. So it's like the slowest gear in the whole AI machine.
Yeah, exactly.
And in this deep dive, we're going to be your guides to figuring out what's causing these slowdowns
Okay.
and what can we actually do about it.
Right.
We're going to focus on four main things.
Okay.
First, data quality, the foundation of it all.
Right.
Second, how we choose the right AI model. That's model selection.
Uh-huh.
Then there's hyperparameter tuning, which is, well, we'll get into that.
Yeah, the bigging?
And last but not least, managing the costs of all this.
That's essential.
What's really interesting here is this isn't just tech jargon.
No, not at all.
This stuff matters, whether you're in business and thinking about using AI, or you're a tech enthusiast who wants to know how it all works.
It's the foundation.
Or even if you're just curious about the latest and greatest.
Absolutely.
Understanding these bottlenecks, it gives you a real edge.
For sure.
So our mission today is to cut through the noise.
Yeah.
Clear explanations.
Right.
Actionable insights. What's
Actionable.
holding AI back and how do we fix it?
That's what we're here for.
Let's start at square one, data quality. It's the foundation. You've probably heard the saying.
Garbage in, garbage out.
Exactly. Garbage in, garbage out. In AI, it's practically a religion.
It's true.
Bad data in, bad results out. Simple as that.
It's fundamental. And the crazy thing is data quality is a huge problem.
Oh, yeah.
The Harvard Business Review, they found that only about 3% of data in most companies meets basic quality standards.
3%. That's almost nothing.
It's a shockingly small number. And it gets worse. Studies from IBM and Carnegie Mellon, they found that something like 90% of company data is never used strategically.
Wow. So we're sitting on a gold mine, but we're not mining it.
Pretty much.
And it's not just about missing out on what we could do. Bad data costs money.
Oh, absolutely.
Experian Data Quality, they estimate that bad data costs companies about 12% of their revenue.
Think about that. For every $10 a company makes.
More than $1 is lost because of bad data. Ouch.
Ouch is right. And there are a lot of ways data can be bad.
It's not just typos, is it?
No, it's way more than that. One of the big ones is data bias.
Data bias.
This happens when the data we use to train our AI doesn't really reflect the real world.
Okay.
Or it has existing prejudices baked in. And there are different types of bias.
Like what?
Well, there's selection bias.
Selection bias.
That's when the data we collect, it isn't a good representation of the population we want our AI to work with.
So, like, if you were building an AI to recognize different birds,
Right.
but all your training images were from, let's say, just North America,
Exactly. It might be great at recognizing North American birds.
but totally clueless about birds from, say, Africa.
Exactly.
So how do we even begin to tackle this data bias problem? What are the different kinds of biases we should be watching out for?
So besides selection bias, there's confirmation bias,
Confirmation bias.
where the AI, it kind of doubles down on existing patterns in the data, even if those patterns are wrong or unfair.
I see.
So imagine an AI trained on old loan application data, where, for whatever reason, one group of people got approved more often.
Uh-huh.
The AI might then unfairly favor that group for future loans.
Oh, so it perpetuates the existing bias.
Exactly.
That's a scary thought. It shows how AI can actually make inequality worse if we're not super careful.
Right. It's a real concern. And that's why understanding the nuances of these different biases is so important.
So we've talked about selection bias and confirmation bias. What other types of data bias should we be on the lookout for?
Well, there's measurement bias,
Measurement bias.
which is when the way we collect data, it spews the results.
Okay.
Like, say, a medical device is more accurate on certain skin tones.
Uh-huh.
The data from that device is going to be biased.
That makes sense.
Then you have stereotyping bias, where the AI learns harmful stereotypes from the data.
Right.
And then there's outgroup homogeneity bias.
Outgroup.
Homogeneity bias, it's where the AI treats people from certain groups like they're all the same,
Oh, wow.
leading to bad predicaments.
And these biases can really mess things up in hiring, in healthcare, even in the justice system.
Absolutely. The consequences can be serious.
It's a big reminder that we need to be really, really careful about the data we use for AI. Another big challenge is missing data.
Oh, yeah. That's a clack.
In big data sets, you're almost always going to have some gaps.
It's inevitable.
So how do we deal with that?
Right. Well, missing values. They happen for all sorts of reasons.
Sure.
Maybe someone skipped a question on a form. Maybe there was a technical error. Maybe the information just wasn't there.
Right, right.
And the interesting thing is, there are different patterns to how data goes missing.
Oh, really?
Yeah. Sometimes it's totally random. We call that MCAR, missing completely at random.
MCAR.
But sometimes it's related to other data, but not the missing value itself. That's MAR, missing at random.
Okay. MCAR, MAR.
And then there's the tricky one, MNAR, missing not at random.
MNAR.
That's when the reason the data is missing is related to the missing value itself.
Ooh, that does sound tricky.
It can be. So how do we deal with these missing pieces?
Yeah, what do you do?
Well, one way is to just delete anything that's missing data.
The whole entry.
Yeah, sometimes even whole columns.
Seems a bit extreme.
It can be. You lose a lot of information that way.
And you might introduce bias, right?
Exactly. If the missing data isn't random, deletion can skew your results.
So what else can you do?
There's imputation,
Imputation.
where you try to fill in those missing values.
Like, how?
Sometimes you can just use the average value for a column.
If it's numbers, yeah.
Right, or the most common category if it's not. There are fancier ways too, like forward filling or backward filling.
Forward filling.
Backward filling, you can use interpolation for time series data,
Okay.
or even train a whole separate AI to predict the missing values.
Wow.
And for categories, sometimes just adding a new category like unknown can be helpful.
Interesting.
The key is to choose the right method so you don't mess up your results.
Right, because trying to fix the problem could actually create new ones.
Exactly. And we need to think about the ethics too. Could your method unfairly impact certain groups in your data?
It's a lot to consider. And when it comes to AI models that learn from labeled data,
Right.
making sure that data is labeled consistently is key.
Absolutely. If different people are labeling the same thing in different ways,
The AI is going to get very confused.
it's like trying to learn a language where the words change meaning randomly.
So how do we make sure everyone's on the same page when it comes to labeling?
The first step is having crystal clear instructions.
Like a really detailed rule book.
Exactly. You need precise definitions for each label, specific criteria,
Okay.
and a clear plan for those tricky edge cases.
Right. Make sure everyone's speaking the same language, so to speak.
Exactly. And then you need to train your annotators really well.
The people doing the labeling.
Right. Everyone needs to understand the rules and be consistent.
Makes sense. What about quality control?
Absolutely crucial. Regular checks and ideally some automated checks too.
To catch any inconsistencies.
Exactly. And you need to measure something called inter-annotator agreement.
Inter-annotator agreement.
It's basically how much different annotators agree on the same data.
Makes sense. So the higher the agreement.
The better. And when there are disagreements, you need a clear process for resolving them.
Like a tiebreaker.
Exactly. Maybe a majority vote or an expert weighs in.
So even though technology is getting more advanced, high-quality labeled data still requires a lot of human effort.
It does. It's a big job, but it's absolutely essential.
Now, how do we catch mistakes that might have slipped through, those mislabeled bits of data?
Good question. There are some techniques for that too. Visualizing your data can help. Sometimes you can spot outliers that look wrong.
Okay.
Domain experts can also help. They can often spot errors that algorithms miss.
Right, because they have that deeper understanding.
Exactly. And you can use statistical analysis to find anomalies or even use machine learning to find potentially incorrect labels.
So we can use AI to clean up AI's own training data.
Exactly. It's like having a robot proofreader for your data.
I like that. It sounds like there are a lot of moving parts when it comes to data quality. What sort of tools are out there to help us manage this whole process?
Luckily, there are more and more tools coming out all the time.
Oh, good.
There's data cleaning software like OpenRefine, WinPure,
Okay.
and numerous. They can help find and fix errors, get rid of duplicates, all that good stuff.
So it's not all manual work anymore.
Definitely not. And then there are data validation frameworks, things like Pedantic, Marshmallow, Great Expectations, and Panera.
Okay. What do those do?
These frameworks let you set rules about your data, like what format it should be in, what the quality should be.
So you can catch problems before they become big headaches.
Exactly. And the really exciting stuff is happening with AI-driven solutions for data quality.
AI to fix data quality problems. Very meta.
Right. This includes things like automated data profiling and cleansing. Smart data integration, basically combining data from different places.
Right.
That better data governance, using AI to make sure data quality standards are met, and even creating synthetic data.
Synthetic data.
Fake data, basically. It can be really helpful when real data is scarce or sensitive.
So AI is becoming its own data quality watchdog.
You could say that.
Okay, so we've covered data quality, the foundation.
The bedrock.
Now, let's move on to the next bottleneck. Model selection. There are so many AI algorithms out there.
I know, right? It's exploding.
Oh, how do you pick the right one for your problem? It's kind of overwhelming.
It can be, but it doesn't have to be a guessing game.
So how do you cut through the noise?
You've got to start by understanding exactly what you're trying to do.
What's the goal?
Exactly. Are you trying to classify things? Are you trying to predict a number, like a price or a temperature? Or are you trying to find patterns in data that hasn't been labeled? Each of those tasks needs a different type of algorithm.
Makes sense. You wouldn't use the same tool for every job.
Right. So after you figure out your task, you have to look at your data.
Okay.
What kind of data is it? Numbers, text, images, audio. How much data do you have? What format is it in? And going back to what we talked about earlier.
Data quality.
Exactly. How good is your data?
You wouldn't use an algorithm for pictures to analyze a spreadsheet of numbers.
Exactly. That's like trying to use a hammer to screw a light bulb.
Right. And then you need to think about how you're going to measure success.
Right. What does good look like for your AI? Are you aiming for high accuracy? Or is it more about minimizing certain types of errors?
You have to define what winning looks like.
Exactly. Then you've got practical things to think about, like where your AI is going to run.
Oh, right. Like in the cloud on big servers?
Yeah, or on a phone or a little device.
So even a really fancy, accurate AI is useless if it's too slow.
Exactly. You might need an answer right away.
Real time.
Right. And then there's interpretability.
Interpretability.
You need to understand why your AI is making certain decisions.
Oh, interesting.
In some fields, like medicine or finance, that's really important.
You need to be able to explain the AI's reasoning.
Right. Simpler models, like decision trees or linear regression.
Okay.
They're usually easier to understand.
Transparent.
But more complex models, like deep neural networks, they could be like black boxes.
You get a result, but you don't know how it got there.
Exactly. And don't forget about the computing power you have available for training and how fast you need this thing up and running.
So many things to consider. I've heard about this trade-off between how well an AI performs and how easy it is to understand.
Right. The classic interpretability versus performance dilemma.
Can you unpack that a bit?
Sure. So often, the more complex models, especially the deep learning ones, they can be super accurate.
Especially with lots of data.
Exactly. But they're often really hard to understand, like how they actually make their decisions.
It's like magic.
Kinda. Simpler models, they might not be as accurate.
Okay.
But they're easier to understand. You can see how they work.
So you might get a slightly better score with a complex model.
Right.
But you have no idea what's happening under the hood.
That's often the case. And that lack of interpretability can be a real problem, especially in situations where you need to be able to explain things.
High-stakes situations.
Exactly. Like if you're using AI to make medical decisions, you need to be able to justify why the AI recommended a certain treatment.
Right.
Thankfully, there are techniques like SHAP and line that help us understand these complex models a little better.
Oh, good.
They give us explanations for individual predictions, and researchers are always working on building more interpretable models.
So maybe we can have our cake and eat it too. High performance and transparency.
That's the goal. Now, you mentioned something about compound AI systems earlier.
Right. What makes those so complex?
Well, this is getting really interesting with these large language models. The LLMs,
LLMs, right?
compound AI systems, they use multiple AI models together. Often LLMs are part of the mix.
Okay.
The idea is they can tackle bigger, more complex problems than a single AI could handle on its own.
It's like a team of AI specialists.
Exactly. But that makes choosing the right models much harder.
Right, because now you're not just picking one.
You're picking several.
And you have to make sure they all work together.
Exactly. The number of possible combinations, it explodes.
Exponentially.
Right, so finding the best combination.
That's a nightmare.
It can be. But there's research happening to help with this. One example is the LMS selector framework.
LLM elector. What is that?
It's a really clever approach. The basic idea is if you can improve how the individual parts of the system work, the whole system will work better too.
Okay, that makes sense.
And LLMs are actually pretty good at figuring out which other LLMs might be good at certain tasks.
So you can use an LAM to pick the best LLM for the job.
Exactly, and that's what LLM selector does. It picks one part of the system, then uses an LLM to suggest the best LLM for that part.
And it keeps doing that.
Until it can't improve things anymore. It's actually been shown to work really well.
That's amazing. So to sum up model selection, what's a good roadmap for actually making that decision?
It all starts with a clear understanding of your goals. What do you need this AI to do? Then you really need to analyze your data. What's it like? What are its limitations? Next, think about the practical stuff. How fast does it need to be? How much computing power do you have?
Right.
It's helpful to think about whether the patterns in your data are simple or complex. That can guide your initial choices.
Okay.
And then, the most important part, try different models.
Experiment.
Exactly. See how they perform on a separate set of data. And don't forget about interpretability, especially in sensitive areas.
Where you need to be able to explain the AI's reasoning.
Exactly. In the end, you want the model that balances performance, accuracy, cost, and interpretability.
Right. The best fit for the job.
Exactly. It's not always easy, and you might have to go through a few different models before you find the right one.
So we've carefully chosen our model. What's next?
Now comes the part some people might think is tedious, but it's just as important.
Okay.
Hyperparameter tuning.
Hyperparameter tuning. For those of us who aren't machine learning experts, can you break that down? What are these hyperparameters and why is tuning them such a potential bottleneck?
Imagine these hyperparameters as the knobs and dials that control how your AI learns.
Okay.
You set them before you start training.
Not during.
No, before. And they affect things like how complex your model is, how fast it learns, and how well it learns from the data.
So they're kind of like the settings that determine how the AI learns.
Exactly. Now, these hyperparameters, they can have a ton of different values, and complex models can have a lot of hyperparameters.
Okay.
So trying to find the best combination, it's like trying to find a needle in a haystack.
A very, very large haystack.
Exactly. And this is what's called the curse of dimensionality.
Curse of dimensionality. Sounds intense.
Basically, as you have more and more hyperparameters, the number of possible combinations
It grows out of control.
way out of control. It could be exponential. You could have dozens, even hundreds of these hyperparameters, each with a bunch of different possible values.
So trying to find the perfect combination.
Manually, it's practically impossible.
Right.
Plus, each time you want to test a combination, you have to train the whole model again.
Which takes time and computing power.
And can be really expensive, especially with these huge data sets and complex models.
So we've got to find the right hyperparameters, otherwise the model won't work well.
Right. It can underfit, meaning it's too simple.
Doesn't learn enough.
Or it can overfit, meaning it memorizes the training data, even the mistakes.
Oh, so it doesn't generalize well to new data.
Exactly. Which means it's not very useful in the real world.
So those tiny little hyperparameters,
They have a huge impact.
they make or break the whole thing. Luckily, there are tools that can help. Our sources mentioned automated techniques for hyperparameter tuning.
Oh yeah, those are lifesavers.
Tell me about them.
So first there's grid search,
Good search.
where you basically list out all the values you want to try for each hyperparameter, and the algorithm tries every single combination.
Okay, thorough, but maybe not the most efficient.
Right. Then there's random search.
Random search.
It's similar, but it randomly picks combinations instead of trying every single one.
Okay.
Bayesian optimization's a bit smarter. It uses probabilities to guide the search, focusing on the combinations that seem more promising.
So it learns as it goes.
Exactly. Then there's gradient-based tuning, which uses calculus to figure out the best direction to move in.
Calculus.
Could be pretty effective. And then we've got evolutionary algorithms, which are inspired by, well, evolution. They kind of evolve a population of hyperparameter combinations, getting better and better over time.
Survival of the fittest hyperparameters.
Exactly. And hyperband is a cool method that combines random search with early stopping,
Early stopping.
which means it quickly gets rid of bad combinations and spends more time on the promising ones.
Efficient. And what about designing the AI itself?
Right, there's something called neural architecture search, NAS for short.
NAS.
It actually tries to automate the design of the neural network itself.
Wow, so it's like AI designing AI.
Exactly. It's pretty cutting-edge stuff. So, yeah, there's a whole bunch of ways to audit this process.
It sounds like an AI toolbox. Are there any libraries or tools that are particularly good for all this automated tuning?
Oh, absolutely. Optuna and Raytune are two that are really popular and flexible.
Optuna, Raytune.
They have all sorts of these techniques built in, making the whole process much easier. You can define what values you want to try for your hyperparameters, and then let them do their magic.
So much better than doing it by hand. Any expert tips before we dive into this automated tuning process?
A few things to keep in mind. First, establish a baseline.
A baseline?
Yeah, so you know how much your tuning is actually helping. You can use a simpler model or your chosen model with default settings just to get a starting point.
Okay, so you have something to compare to.
Exactly. Second, and this is crucial for all of machine learning, make sure you've split your data into training, validation, and test sets.
Right.
Use the validation set to test different hyperparameter combinations during tuning.
So you don't accidentally overfit to your final test data.
Exactly. Third, use early stopping. If your model stops improving or even starts doing worse, stop the training early.
Saves time and resources.
Yep. And last but not least, make sure your entire training and evaluation process is set up right before you start tuning.
Solid advice. Set yourself up for success from the start.
Exactly.
Now, let's talk about the final piece of the puzzle. Cost management. AI can be expensive.
Oh, yeah.
Where do the costs usually come from, and how do we keep them under control?
This is a big one, especially as more AI is running in the cloud.
Right.
Managing cost can literally make or break an AI project. One of the biggest expenses is the computing power for training and inference.
Inference.
That's when you use your trained AI to make predictions on new data. And training these complex models, especially deep learning ones, it often needs specialized hardware, like GPUs and TPUs.
GPUs, TPUs.
They're powerful, but they're not cheap, especially in the cloud.
So the more complex the model, the higher the bill.
Basically, the size of your model and how much data you're training on. Those are the big factors.
So how do you manage those costs?
Well, you can try to use more efficient models,
Okay.
right-size your computing resources so you're not paying for more than you need.
Makes sense.
Take advantage of things like spot instances. Those are cheaper but could be interrupted.
Okay.
And there's a whole set of practices called FinOps.
FinOps, we touched on that earlier.
Right. It's all about bringing financial accountability to cloud spending.
Makes sense.
It's about getting finance, engineering, and operations teams all working together.
To make sure they're not overspending.
Exactly. You need to understand where your money's going, set budgets, optimize how you're using resources, all that good stuff.
It's about being smart with your cloud budget. What about other costs?
Data storage is a big one.
Oh, right. AI needs a lot of data.
Tons of it. And storing all that data, especially in the cloud, it can get expensive.
So what can we do about that?
You can compress your data to make it smarter.
Okay.
And you can use data tiering, which means you move data you don't use often to cheaper storage.
Smart.
You also want to have good data management policies and make sure you're using the data you already have before buying more.
So being strategic about your data lifecycle.
Exactly. From how you collect it, to how you store it, to how you eventually archive it.
It all adds up.
It does. And then there's the cost of human expertise.
Oh, right. The people who build and manage these AI systems.
Exactly. Good AI experts are in high demand.
They don't come cheap.
Nope. So companies need to think about how to manage that cost.
Like what? Training programs for existing employees?
Exactly. Building internal expertise can save money in the long run.
So it's not just about the technology costs, it's about the people too. Our sources also talked about cloud cost optimization tools.
Oh, yeah, those